Okay, good morning, everybody. Let's get started. Today, happy Friday, our fifth class. We're going to talk about the derivative function. We saw that word for the first time last class. Just while we've got our calendar up here, looking ahead, on Monday, we're doing introduction to derivative formulas, and then Tuesday is polynomial optimization problems. We'll talk about that. But I want to point out that I said Tuesday, I think I meant Wednesday. Friday coming up, you are going to be assigned your very first quiz. It is a take-home quiz. I will give you more details about it, on the Wednesday, but I will hand it to you a week from today. You'll take it over the weekend individually. This is on your own, and I'll talk about like what resources you will have with you, like while you take the quiz. It's not really like something to super stress about, but it is going to be on lessons 1 through 7, and the best way to prepare is to go through the homework, just to do the homework and maybe review anything that seems tricky to you. Okay, so that's coming up a week from today. I will hand that to you. Also, a week from today is our first project check-in day. I have no agenda on that day. You are just going to come in and work on the 2 projects with your classmates and with me. I will walk around and help, but I'm not going to stand up at the front of the room and do anything for the entire class. In order to get the most out of that day, you are going to want to be on track according to my recommended calendar for the project. Okay. All right. Before we jump in on page 28, one quick announcement about a scholarship. Some GCC student is going to get $1,600 about a month from now, but almost everybody is excluded from this. So let's just see if it happens that anybody meets the trifecta in this room. You need to be a new GCC student, new this semester. You need to be a single mother. You need to have a GED. If all 3 of those apply to any of you, see me after class and I'll give you the details. So page 28 is one of the things from the activity from last class, but I just want to highlight that we did like the same problem twice, and I want to make it clear what the difference is between the 2 things. In this problem, it said find f prime of 2 for this function, 1 over x squared, by using a table of values on your calculator. So I've done some of the work here. I didn't really use a table. I just did 2.001 compared to 2, and then just did the slope of my secant line, and I said, hey, that's probably pretty close to the slope of the tangent line, which is what f prime of 2 stands for. On my calculator, I got negative 0.2498. That's going to be really close to the right answer, which turns out to be exactly negative 1/4, negative 0.25. So we are calculating the derivative here numerically, and it is an approximation. So this is a numerical derivative. But on the very next page, it said, hey, do the same problem, f prime of 2, but this time don't plug in a specific age. Don't pick 0.01 or 001. But instead do the hardcore algebra. And so I got it started here. All of the algebra is actually written in the answer key. And at the very end of the day, you are going to get exactly negative 0.25, exactly negative 1/4 here. And this is the algebraic derivative. And so like it kind of looks funny to see the same question twice, but you're attacking the same problem in 2 different ways, numerically and then algebraically. And I want you to be able to do both. So I just wanted to make that clarification for those two different ways to think about the same problem. Okay, so we are on now page 31, so jump ahead, 31. And I will point out that we have seen this thing before. It has a name, that's the difference quotient, and it represents the slope of a secant line connecting a particular point to a point that is h away from that one. So we move over a little bit. H is how much we move over. And what we'd really like is for that secant line to turn into a tangent line. And we just throw a limit, make the h, the horizontal, change really small, and the secant line morphs into the tangent line. And we gave it a name. We called it the derivative. And we gave that little apostrophe. We called that a prime. So that just stands for the slope of the tangent line at a particular a. But how about we generalize this a little bit more, and instead of a particular a, we're going to generalize it to like any generic x value. And so if you look at the next thing, right down here, you'll see exactly the same formula, but all of the a's have turned into a more general x. So going from a specific a value to a more general x value. And this new formula is not called the derivative of a function at a point, but rather just the plain derivative of the function, like the overall derivative of the entire function at every single x that we can name. So let's take a look at how we would go about graphing y equals f prime of x. We are looking at the graph of y equals f of x. I'll label this just to be clear. And what I'm interested in plotting over here is the graph of y equals f prime of x. Okay, so we're going to try to graph this function, which calculates at every point on the original graph the slope of a tangent line. So we're going to plot the thing which represents the slopes of all the tangent lines. So when I do this, I first start with my points that are horizontal. How many horizontal points do you see in the original? 3, right? I'm looking for places where the tangent line is perfectly flat, perfectly horizontal. On the very first day of class, we actually called those critical points. I think we'll see that formal definition soon. But if I take a look at those 3 points, and I draw 3 little tangent lines at those points, technically the tangent lines go forever, but I don't want to clutter up my picture, so I'm drawing small tangent lines. And I know that the derivative is the slope of the tangent line. What number is the slope of those 3 lines? M equals 0, M equals 0, M equals 0, okay? And now we're going to pick another point. Just going to pick a point, I don't know, let's call it right there. Just trying to pick something left of that first horizontal, any place left of the first horizontal. And then I'm going to draw a very, very rough tangent line. I'm not even going to use a straight edge, and you don't need to either. But just draw something here that just barely touches the curve and then runs away. Something like that. And I see it is pretty steep, and it is downhill. What kind of a slope am I going to have there? Negative, because we're downhill. And it's pretty steep, so it's going to be a fairly big negative number. I don't know, like I'll actually count boxes here. Like I guess I need to draw my line a little bit further if I'm going to count boxes. So I don't know, how about we call it like there, and then maybe like the original point there. So how many did I fall? Looks like 5, and then over 1. So what's the slope there? -5. And I really want you to just like ballpark it very quickly. So don't sit there counting a lot of boxes and coming up with like super accurate estimates. Just rough here. Okay, now let's pick a point between the first 2 horizontal ones. We'll do this guy in purple here, about right there. And then just a very quick tangent line, something like that. This one is going to be pretty close to the curve for a while. And here I'm not even going to count boxes. I'm just going to compare to the slope that we wrote there. Positive or negative for the new one? Positive, more or less than 5. Maybe a little less. It's not quite as steep as that one. I don't know, 3, 4, whatever we want to say. Let's call it 3. Okay, and let's do it again here. I'll draw a little tangent line there. Positive or negative? Negative. More or less than, say, 3. What do you think? I feel like less than that 3 is not as steep as that one. I don't know, 1, 2. Very rough estimates here. And then I'll pick one more. Let's pick one right there at the end. Positive or negative? Positive, big or small? It's pretty big. Maybe it's like the mirror to that 5 one over there. Let's call it 5. If you call it 4, no problem. If you call it 1, I don't think it's a 1. Okay, so we've got all of these points over here. We are graphing the derivative of that function. The derivative, remember, has an input of an x value and an output, the slope of the tangent line. Input the x, output the slope of the tangent line. At this very first point right here, we input the x. What's the x? -2. We output the slope of the tangent line. What's that? -5. So you are plotting a point over here. Input -2, output -5. You just plot that point. -2, -5, slightly off my picture. Input the x, output the slope. Next one is my horizontal down here. Do this guy in. Okay, input the x, what is it? -1, output the slope, 0. Plot the point -1, 0 on our new graph over there. -1, 0, right there. Okay, let's try the other ones real quick here. Input the x, 0, output the slope, 3, 0, 3. Here. Next one is up on top. Input the x, maybe 1.5, 1.4, something like that. Output the slope, 0. So like one and change with 0. Okay, 3 more. Input the x, 2. Output the slope, -1, 2, -1. There. And I know we're going quick. Let's do these last 2. Input the x, 3. Output the slope, 0. 3, 0 is here. And the far right point, input the x, 4. Output the slope, 5. 4, 5, slightly off my picture. There. And these are just, I don't know, seven points that are on the graph of the derivative function, but we're going to connect them with smooth curve. So let's connect with the smooth curve. Something like that. Yeah, you got to do the sound effect. I hope the microphone picked that up. That was quality. Yeah, so that's the graph of the derivative. Notice it's real easy to plot the x-intercepts on your derivative because those are the places where the graph is flat. That's always where I start. So like I divvy up my original graph at the flat places, and then I pick points in between the flat places. And also, just want to point out, like way up here, do we know that that point is supposed to be the highest point? We just picked like a sort of random point. That point right there was this guy. In order for that to be the highest point on the derivative, this needed to be the what? Steepest, right? The biggest slope, the steepest line. I didn't go out of my way to pick the steepest line. I just sort of picked a random point in there. So I just want to make sure, like, I'm not going to take points off, I guess, if you turned it around right there, but you are reading more into your point than is actually there, right? Like, all I know is I'm supposed to hit these points. I got to turn around someplace. At the moment, I don't have a precise way to do that, like to know where to turn around. So just turn around somewhere. Okay, so that's good. So again, the key here is that when you're graphing the derivative, you are inputting the x and outputting the slope. Okay, based on the graphs above, let's guess the degree of f. That was the original degree of the left-hand graph. What do we think? Maybe 4? Yeah, I mean, like I see 3 turning points, 3 places where the graph is flat. And I see that on the far right and far left, the graph ultimately is going in the same direction, both up to -infinity, as opposed to like 1 up and 1 down. So that makes it an even thing. Okay, so 4 seems reasonable. I mean, it might be 6 or 8, but we'll say 4. And then same question on the derivative. Graph of the derivative. What degree do we think there? It's odd because we're doing different stuff, and maybe 3 because it's got 2 of our turning points here. 3. Okay, and so we'll soon see that for any polynomial, the degree of f prime has a very specific relationship to the degree of f. What do you think you have to do to the degree of f to get the degree of f prime? It's 1 less. 1 less. The degree of f is 1 less. F prime is 1 less than f. Yeah, so we'll see that soon enough. If you have seen calculus before, you might have like a rule in your brain where there's like an n-1 inside of a derivative calculation. That's it right there, 1 less. Okay, we're going to do things a tiny bit different today. We're going to do 2 demos and 2 activities. So you're going to start with this activity here. And with about 30 minutes left in class, I'm going to call you back together and we'll do another demo and then another activity, okay? Go quick with your tangent line, your derivative graphs. Very rough estimates. Don't get hung up on these first 2 problems. 4. So I've started problem 4 from the activities up here. This is a tough one algebraically. Let's do some highlights. So the question says find f prime of x. Very soon we're going to have shortcut ways to do this, but right now all we have is our limit definition. It's complicated. So I've written the definition out in the first row, and then I have substituted. F of x is just square root of x. So I've just copied that in the second slot. And then f of x plus h, I just replace the x with x plus h. So it's square root of x plus h, all inside that square root, all divided by h. So the technique here to clean this thing up, What I'd really like to do is plug in h equals 0, but I cannot right now because that's division by 0. The top also turns out to be 0. We need to do work to resolve that before I can plug in h equals 0. And the technique here is to rationalize that radical. Wherever it is, it doesn't matter. I know typically you get radicals out of the bottom, but you can get them out of the top just as well. And so we multiply by the exact same thing, but change that sign in the middle of the two radicals. So multiply top and bottom by the conjugate of wherever the radicals are. Okay, so we're multiplying fractions, so we're supposed to multiply across the top and multiply across the bottom. On the bottom, I'm actually not going to do any work. I'm just going to rewrite it. Don't distribute down there. You'll see why it's better to leave it that way, undistributed, in a moment. But multiplying across the top, we are going to distribute, and lots of good things are going to happen. So when I multiply, so we're doing FOIL up here, right? So first times first, what do you get? X plus h, right? Those radicals just cancel very nicely. Then I do the outers. I get plus root x times root x plus h. I'm not going to do anything else with that. It's just literally writing the outers. Inners, what do you get? Minus root x times root x plus h. Hey, that's convenient. And then the less, what do you get when you multiply these? Negative x. Negative x. Okay, so good stuff happens right here. So the radical x plus h cancels. It just subtracts off. That's the whole purpose of that multiplying by the conjugate. And then something else cancels. What else cancels? The x's cancel, so that's just like convenient. That's sort of a pleasant surprise. So the x's go away. And then all that's left on the top is h. And hey, there is an h sitting there on the bottom waiting to cancel with that h right there. And so that is why we did not distribute on the bottom. That h right there eventually is going to go away. So that means there's nothing left on top, which means I need to introduce a placeholder. So we'll put a 1 up there. Okay, so this is kind of a mess. I'll rewrite it. Limit h goes to 0 of 1 over root x plus h plus root x. It canceled with the h there. Yeah. Exactly. Yeah. Okay, and now finally, I've got a brand new limit, and whenever I see a new limit, I try plugging the thing in. So I'm just going to literally plug in h equals 0 and see if we get something that's well defined. So when we plug h equals 0 in, 1 over square root of x plus 0 plus the square root of x. Notice that I was really careful to write limit in the front of all of them until right there, because that's the step where I literally send h to 0. And then we just clean things up on the bottom. 1 over what? 2 square root of x, right? That's just square root of x plus square root of x. Good, that's our answer. For that function that we started with, 1 over, square root of x, the derivative is f prime of x equals this thing we just found, 1 over 2 square root of x. Okay, so the bad news is this calculation is tougher than if we had changed x to a particular number like 1 or 5, right? Like it was harder for us to do this calculation with x's. But the good news is that we can now find the derivative for that function at any x value we want. It's as simple as evaluating a function. And so down here it says, hey, why don't we just find f prime of 1? So let's write it. F prime of 1 equals, that's your formula. I'll copy it here. This is f prime of x. So f prime of 1 is 1 over 2 square root of 1. It's just a function now, right? I mean, it's a derivative, but it is in itself a function. So we just plug in. 1 over 2 square root of 1 is just 1 over 2. And so what that means, you had a picture of this function on the previous page. I don't think I told you that it was the square root function, but if you go to the bottom of the previous page, that's the square root of x that I graphed right there. And so what does this mean? This means at x equals 1, the slope of that tangent line is a half. You might have estimated that slope just visually, but now we have learned at x equals 1, the slope of that tangent line is exactly half. And it's really easy to now find the slope at any point. Let's do the next one, f prime of 4. 1 over 2 square root of 4, which is 1 over 2 times 2, which is 1/4. On the picture on the previous page, at x equals 4, the slope of the tangent line is 1/4. And it's like instantaneous because we did the hard work for x instead of a specific number. That's the idea. Okay, so there is this thing called the power rule. We'll see it in a coming class. Actually, it might be next class. But here it is. It says if you happen to have a function of the form x to a number, and there's a real quick shortcut. It says that the derivative is n, that's the power, times x to the 1 less than the number. We'll see it soon, but for right now, let's just sort of use it. If we start with our function, square root of x, okay, in order to use this rule, I need to get my function to look like x to a power. Square root is really x to what power? It's positive 1/2, right? And then according to this brand new rule, f prime of x is equal to, what I'm supposed to do is take that power, plop it right down in the front. So what number am I bringing down in the front? 1/2 comes in there. I copy the x, and then I subtract 1. It used to be n, but now it's n minus 1. Subtract 1 from that power. So what's the new power? Negative 1/2, right? Right, we just subtract 1. It was 1/2, we subtract 1, you get negative 1/2. Okay, so that answer is fine, but let's clean it up just a little bit. 1/2, 1/2. X to the negative 1/2 really means x to the half downstairs, right? So x to the half right there, right? That's the negative part of the exponent. But x to the half really means there's a radical. So this is just square root of x, right? And 1 over 2 square root of x, that was the right answer. Like we got to the right answer in the only way we know how. But very soon, we're going to have a bunch of shortcuts that allow us to zip to the answer quite quickly. So that's the first one we'll see. Okay? All right, and we can also get the calculator to help us out, the graphing calculator, I should say. Again, I don't need you to like buy a graphing calculator, but if you happen to have one, this is how you do it. You don't need to take it out now. I'm going to do this real quick. But, one way to get the calculator to tell me these answers up here is to type in this thing. I'm doing this on the video so you can watch it slower later on, but it's inside of math. I'm trying to get the screen to look like this. If we scroll down, I think it's number 8. N-deriv, that stands for derivative. And then I'm typing my function. My function, the original function was the square root of x, comma, and then you just put an x every time. It's kind of wonky, but you just put x every time there, comma, and then if I'm interested in the derivative at x equals 1, I put a 1 here. What did we calculate for the derivative at x equals 1? It was 1/2. Okay, here we go. 1/2, well, close. The calculator does not know any calculus. The calculator doesn't know how to do a derivative. What it's doing is a secant line for 2 points that are really close to each other right on x equals 1, and it's not perfect. Let's try the other one, f prime of 4. It's exactly the same command, but just at x equals 4. What am I expecting as my answer? Quarter, so what should the calculator tell me as a decimal? 0.25, so it's pretty good.
How did you get it to copy your...
Second entry. We'll copy the previous line. Second entry, again, we'll copy the line before that. You can go back pretty far. It's something like 20 different commands that you got in there. All right, so I think that's good. There is another way to get the calculator. Well, all right, let's do this. I think this is worth it too. This is all written up in detail here, but if you type your original function here, square root of x, let's just get it to show us that one. So 0 to 10 is good, and then 0 to 3. Okay, so here's the square root function. Looks a lot like the one. Did I do something wrong? This is not what I was expecting to see. 0 to 3. Okay, there we go. All right, so this is what your previous page looks like. That's the graph I gave you, and then I asked you to graph the derivative. So we can ask the calculator to find the derivative by by putting n deriv right here. So it's inside of math, it's still number 8. And then we type in, okay, so you could just type square root of x, but it's actually nicer to tell it y1. And then if you happen to change square root of x, it'll update it, it'll know whatever's in y1. So the commands are over here, but anyway, it's inside of variables, and then it's up here, y variables, we go to the right, and then it's the first one function, and then there's a list of all the different ones. The function is currently living in y1, so I just hit enter right there. And so that's going to say take the derivative of whatever was in y1. I said it's kind of wonky, you always put a comma x, and then you put comma the number, but I don't want it to just do one number, I want it to graph all numbers, and so I actually put in x again as my way of saying, hey calculator, do all of the numbers, okay? All right, so it is now going to again graph the square root function, and then this is what hopefully you drew second, something like this. You ever seen the calculator fumble for as long as it is right here? Right, it's going pretty slow, isn't it? Because it doesn't know what it's doing. It is literally calculating the slope of a really good secant line at every pixel. And it takes time for it to do that calculation for every single pixel. Yeah, so that's good. All right, next page. 2 pages from here. 35. Okay, so some vocabulary. A function is said to be differentiable if its derivative exists. Differentiable means the derivative exists. And it's been so like nice and friendly today calculating derivatives, we'd think, well, how could a derivative possibly not exist, right? We just do the process that we did numerically or algebraically, and you get your answer, right? So how could it fail to exist? So at its heart, the derivative is a limit. And we talked about limits a few classes ago, and there are a couple of fundamental ways in which a limit can fail to exist, right? You could have like a jump, right? I guess that's really the main way. Otherwise, I think that was the main way, like for us to have a jump. And so it turns out there are a few basic ways for the derivative to fail to exist because the derivative is a limit and limits might fail to exist. So here's one. If you happen to have a corner, maybe more mathematically a cusp, but you've probably seen the word cusp in a non-math context. Like if you're on the cusp of some discovery, you're right there, you're right on the edge. Same kind of image. So the derivative fails to exist here, and here's why. We know that limits say you got to get the same number from the left as from the right, yes? Better have the same number, and that's that jump I was talking about. So you better get to the same thing for the limit to exist. Well, if I think about derivatives on the left-hand side of that point, what kind of slopes are these? What kind of numbers? Those are all positive slopes, right? And so like if I were to like draw the quote last one, I mean, there isn't a technical last one, but it's roughly that, right? And then if I think about approaching from above this point, what kind of slopes are these? Negative, and so like the quote unquote last tangent line there is that. Are you going to get the same slope for your tangent lines coming this way as you are coming this way? No, they're not going to match up at all, right? Whereas if I were to focus on like maybe a nicer point like that guy, I could think about drawing like tangent lines that are approaching this guy, and I get something like that. And then don't they like, okay, so they're a little smaller here, but then don't they eventually merge to like the same tangent line, no matter which side of the point you're on? But that's not what happens here for my corner. So if you have a corner, derivative does not exist just at the one spot, just at that one point. Derivative exists perfectly well at all of the other points on this graph. Yes, which just means it's going to be smooth. It just has to be smooth. And as long as it's smooth, curvy, and not pointy, the tangent lines from the one side will merge perfectly with the ones from the other side. Okay, at this one spot here, we're supposed to see a vertical tangent line. So okay, so vertical lines are no problem. Nothing fundamentally wrong with that. Like that tangent line exists. But we know the derivative is the slope of the tangent line. What is the slope of a vertical line? It is undefined, right? So the derivative, I can't tell you what the number is. Like if you tell me the derivative is some number, I'll say, well, that's a problem because I know the slope is supposed to be undefined. So tangent line is perfectly fine, but the derivative does not exist there because it's undefined slope. Okay, and then finally a discontinuity. Here it feels like at that one spot, even though there's a hole there, it feels like, hey, well, you know, I can draw a tangent line there, and it's got a number. I don't know, the slope is 2, something like that. So it feels like the derivative should have no problems there. I'm not going to get into the whys, but But it turns out having a hole makes this thing fail. And if you want to know why, you can see me after class. But if you are discontinuous at a spot, automatically the derivative has no chance of existing. Okay, those are our three ways, three common ways for our derivatives to fail to exist. Okay, so coming down to this picture, has anybody seen this notation? It kind of looks like absolute value, but it's just got the lines on the bottom and not on the top. That's intentional. Have I seen it? It's called the floor function, and what it just means is take the number that's inside and round it down to the next integer. You don't need to like write that down, but it's anyway, it's a function. Round down, and maybe even round isn't the right word. It's like just go down. So if I said, you know, put like the number 7.2 inside of there, and we round down, what do we get? 7. And if I said 7.8, and we round down, and we get 7. So it's not really rounding according to the traditional 0.5 is the cutoff. Just pull everything down. And so all of the numbers between 7 and 8 are going to get pulled down to a 7. That's why you have like this horizontal string. Everything between 7 and 8 gets pulled down to a 7. But then once you get to 8, what do you get when you, like what's 8? Is 8. And so at 8, it jumps up. Okay, so where are the places where this function is not differentiable? Give me one number. At x equals 8, because there is a jump there. At x equals 1, there is a jump there. At x equals -7, there's a jump there. All of the integers, every integer. But how about at like, I don't know, 1.3? Does the derivative exist at 1.3? Sure, no problem at all. That is a perfectly smooth curve. It's a line, but we'll just call it a curve. At 1.3, it's fine. At 1.4, it's fine. At pi, it's fine. But it's the integers. Those are the jumps. No good discontinuity. How about this fifth root of x function? Where is the problem? At x equals 0, and what's the difficulty? Yeah, so we'll say it's a vertical tangent line. Vertical tangent line. Tangent line is fine, but the derivative does not exist at 0. Okay, and this guy right here, it's a piecewise function. These are just two lines. You can graph them. I'm going to graph them real quick just so you can jump to the activities. But the graph is x until we get to 3. So it looks like that until we get to 3. And then 2x minus 3 from 3 onwards. Okay, so that's the same idea. It turns out it's going to fill in that point, but it's just going to be a slope of 2 instead of a slope of 1. Okay, so that's the piecewise defined function. So that function is perfectly continuous at x equals 3. I can draw that without picking up my pencil. So it is continuous there. But what's the problem with the derivative at x equals 3? It's a cusp or a corner. Right? It is not smooth. It is not curvy at that spot. It drastically changes rules right at that spot. So we'll say it's a corner at x equals 3. Okay, so last thing is just some vocabulary you'll see in your book. You'll hear me say, instead of saying that a function is differentiable at x equals 2, we're going to omit the x part, and we could just say it's differentiable at 2. At 2, we're always talking about at, it's always an x value, it's the input value. You can say that a function is differentiable on an entire interval. That means for every x value between 0 and 5, this function's derivative exists. Or you could say a function is differentiable everywhere, which means that for every single x, the function has a derivative, and we might just say it's differentiable. The function is differentiable, meaning everywhere, no problems at all. Okay? All right. Second activity. It's okay if you didn't quite finish the first one, but just move on right here, everybody. And you are going to draw sketches of derivatives. The first one is supposed to be accurate, meaning exact. The other ones after this first one are just going to be very rough.